All right, let's start today's class. Moving on to a new topic, which is work and kinetic energy. Actually, it's work and energy, but in this specific chapter, we're just going to take a look at kinetic energy, and then we will take a look at potential energy and elastic energy. So different kinds of energies. So let's start by getting into topic here. Oh, laser. Right. So let's talk about what we understand by energy. So we can say that energy, it's the capacity for doing some work, right? And what we understand by the work means it's pretty related to the intuitive definition of work that we have from day-to-day activity. So it's related to some action, and we know that some action is related to a force. So remember, the force was was basically the manifestation of performing an action between objects, right? An interaction between objects. So work is going to be related to that, and energy would be the capacity of performing that work. So energy may exist in different forms. In this particular case, we're going to take a look at the kinetic energy, which is related to motion. But we can have potential energy, thermal, electrical, chemical, nuclear. So different energies related to the origin of the phenomena that defines it, right? So then we can have, for example, heat and actually work. So that's energy related to a process of transferring between two bodies, for example, when we have heat and when we're performing work derivated from a force. So let's take a look at this example here. So a baseball pitcher, it's doing work with this throwing arm to give the baseball a property called kinetic energy. And we'll see, we'll get to that definition down in the presentation. So here we will introduce the concepts of work, energy, and the conservation of energy, and will allow us to deal with problems in which Newton's laws that we've seen so far aren't actually enough on their own. And for now, we will still assume that objects can be treated as particles. So we're not taking into account the shape of those objects, just the mass. So let's consider this first example here. Let's say we have a block which can be displaced over a horizontal plane with a displacement of s. So we're saying that s will be x2 minus x1, right? So s would be equivalent to what we defined before as delta x. So the displacement of that object. So while the object the object is being displaced due to a force which is exerted on it and which is constant and pointing to the right, and that force has the same direction as the displacement. So it's basically it's horizontal, right? It's parallel to the sliding plane, the floor, basically. So we define the work done by this force as the product of the force of the magnitude of the vector, right? And the displacement magnitude. So it's force times displacement. So that's how you define the work that, in this particular case, let's not generalize here. In this particular case, it will be the magnitude of that force multiplied by the displacement that the force created basically on that object. So we can take a look at the units that we have here. So the work will have units of force multiplied by units of length, and that's newtons meters. And that new unit, we will call it joule, and it's symbolized by J. Okay, so the work, it's gonna be measured in joules. Any questions about this example? It's pretty straightforward example, but it will let us define work in a more general way in the next slides. All right. Okay, so let's consider now this other example. So we have a car and we have a person in the back, which is pushing that car. That person is pushing the car, but of course it's not doing it exactly on a straight on the same, the same direction that the car would be moving, right? It's pushing a straight line, but not with the exact same orientation. So the force that the person is exerting on the car has this direction, so it has some specific angle. So if we apply the same reasoning as we already had from last classes, and that we should have incorporated to ourselves when solving problems, then what we would do here is decompose that force into two components of the of that force, right? Which are the projections to our system of coordinates. So let's say we apply a system of coordinate in 2 dimensions. So we have the x-axis and the y-axis, and then we can project the force that the person is exerting on the car into the horizontal direction and to the perpendicular direction to that motion. So this is parallel, this is perpendicular. And we can calculate the component, the parallel component, as f multiplied by the cosine of the angle. We know that. And then we can calculate this other component, the perpendicular component, which is f multiplied by, the magnitude of f multiplied by the sine of the angle, because we need the opposite leg of the triangle. And from this, we can say, as we defined before, that the perpendicular component will not be performing work, right? The work will be performed by the parallel force to the component of the parallel component force, sorry, which is in line with the motion. So if we write this, we will have work equals F multiplied by S, the displacement, X final minus X initial, multiplied by the cosine of the angle. So this is the angle between F and S, the displacement. So remember, these two are actually vectors, right? So the force and the displacement here. And that angle is the same, right? Because the displacement is, is the same as the horizontal. In this case, the horizontal is the direction in which the car is going. So so that angle will be the same f, the same angle defined by s and the vector s and the vector f. Okay, so if we take a closer look at this, we have the magnitude of s, the magnitude of f, and the cosine of the angle, which is defined by those two vectors. And that, if we can recall from the first class about vectors, that's actually the scalar product of those two vectors. And so we can define the work in a more general way as the scalar product, the dot product, whatever you want to call it, between vectors f and s. So that's the actual definition of work in this other case when we have to when we are not strictly talking about just a straight motion. Yes, exactly. Work is not a vector. Work is a scalar. Good, good. Yeah, okay, so Ili's asking, does that mean that work is not a vector? Exactly, yeah, it's not a vector. It's a scalar. Yes. So we can say it's a quantity, right? And it makes sense, right? Because this work, we said that it's related to energy. Actually, it is energy, right? Because energy is the capacity to perform that work, and we will see that they have the same units. So it makes sense that the work is a scalar quantity because it's not pointing anywhere. It's just defined by the the action that force is it's the work that force is performing, right, over that displacement. That's a good question, Ellie. Okay, and so any other questions about that? Is that clear? We have defined the work as the scalar product, right, between the force and the displacement. So it's not force times displacement. It's the scalar product. So geometrically, it's defined by this here, and then we can apply the definition of the scalar product. Okay, so let's take a look at some examples here of work of forces being applied to objects. So let's say we have F and applied to this object, and it's moving to the right. Then then our system of reference is pointing to the right, and then we have positive direction pointing up. So F has a component in the direction of S, and then we can calculate the work as F parallel, meaning, F cosine of the sine multiplied by the displacement, and that will give us some work, and work will be positive. Okay. Let's take a look at the next one. So we have the displacement, same displacement as before, going from left to right, but now we have some force which is pulling the object opposite to the motion. And that could be some tensions, could be some kind of friction, could be whatever thing there. But the thing is that the force is now it's now pointing to the other side, right? So if we decompose that and we apply the exact same reasoning, we do that dot product, that scalar product, then the angle, then we would need to use is this angle, not this little angle here. It's this one. So if we calculate that, then we would have basically the same, but we would have a negative value for the work. Okay. So we will have a negative work in this case. because the object is moving to the right, and then we're performing some action there, and we are basically taking energy from the system. And in this case, we're pumping energy in on the system, right? So here the block is tending to, I mean, we know from Newton's laws that the block will tend to stop, right? Because it's experimenting a force which is on which is on the contrary of the movement, and of course we will have some acceleration in the opposite direction of the displacement, and if we have a velocity, will decrease. So we are taking energy out of the system. And in this other case, we are pulling the object. We'll create some acceleration here, we'll have velocity, and then we'll be pumping energy into the system by means of that force. Okay, can you, this is a simple example, but it's pretty interesting how the sign of the work comes on its own. Basically, you don't need to, of course, you can't think about it, right? If you're pulling from an object which is moving, then you're taking energy out of the system. If it's moving on the contrary to your opposite to the force you're applying, it's intuitive, right? It's intuitive, but the sign of the work will come from the simple calculation of performing the actual scalar product there, right? And let's take a look at this other example here. So if we have a force which is perpendicular to the direction, so we're pulling up, doesn't really matter why, we can have a, let's say, an electrical interaction, we can have a magnet, we can have whatever, could be pulling down too, right? Gravity. So that force which is perpendicular won't be performing any work in this specific motion. Okay, that force won't be taking part at all when the object is moving. So there's no flow, let's say, flow of energy from the system or into the system. And of course, we can see that if we do the cosine of 90 degrees, then we'll get a 0. So f times 0 times f will give us 0 there. So we have no work in this case. And down here, what I'm including is that similarly to what we've done with the net forces, we can calculate the net work. We can calculate the total work that's being performed simply by summing each one of the work done by the forces that are being exerted into the object. So the total work would be the work of the net force, and it will be the sum of each of the forces that are composing that net force. Right? Any questions? Any considerations, concerns? Okay, so let's jump into some problems here. Let me get the board. Just a second. And I'll move to the tablet. Then you stop sharing here. And share Okay, so the problem we're gonna take a look now is problem 2 from the set 4. Do you have that set? Can you tell me that if you? I might not have uploaded it. Let me check real quick. Oh yeah, I think you're right. Well, I mean, we're all in our computers, so I guess you can download it right away because I am uploading it right now. Sorry, I forgot to. I uploaded the lecture app. I forgot about the problem set. It's problem set 4. Chapters 6 and 7. Yes. And let me post it. Okay, should be up. So it's problems, chapters 6 and 7. So if you can download it and give me a thumbs up, would appreciate, and we can continue with problem 2. Actually, I don't know if I can transfer it from. Okay, cool. Because I was about to try to transfer it through Zoom, but if that's not necessary, let's just move forward. Thank you, Dominic. All right. Give it just one more minute to download the problem sets for those who haven't done it yet. Keep going. All right, I'll start by reading it. So it says, this is problem set 4, work and energy. And the problem is number 2. So it says a loaded grocery cart is rolling across a parking lot in a strong wind. You applied a constant force F equal to 30 newtons in the x-axis, or let's say just the one of the axes, minus 40 newtons unity vector J to the cart as it undergoes a displacement. S equals to minus 9 meters in one direction, minus 3 meters in the other direction. All right, so how much work does the force you apply on the grocery cart? Yeah, that do, it's kind of, yeah, that's a typo. Well, okay, so we need to calculate the force that it's being applied, the work that the force does, right? So this one is pretty straightforward in the sense that we are nicely getting the components of the vector F and the components of the vector S. So there is not much that we can do here. So, but calculating the work, that will be the only thing to do. So we have F vector is 30 newtons, I minus 40 newtons J, and we have it's it's S. So S 9 meters, I 3 meters J. And what we want to get here is the work. So work, we said it's equal to F scatter product S dot product, right? So it's the product, the scatter product of those two vectors. And of course, we can do that fairly straightforward, because that would be 30 newtons I, 40 newtons J. Meters I. J. And we know that we can calculate that product vector by multiplying each of the components. So this would be 30 newtons minus 9. Let me just use parentheses because we have a minus there. Plus minus 40 multiplied by minus 3 meters. And this is minus 270 joules plus 120 joules. And that's minus 150 joules. Okay, so there's no secret in here. It's just some vector algebra. It's pretty straightforward. And of course, we can identify this too as the components of the work performed by the force in both directions. Let's say x is vector I and y is vector j, right? Just to be consistent with ourselves. Right, so we have the work, the work there, and then we have that. But let's not get confused here with this fx works fy. So as we said before, work is a scalar. Those two are the work performed but by each of the components of the force. Right? So it's not that the work is a vector and those are the components. Those are those two are the work of each of the components of the force. Okay. I guess that's all for that one. Problem 2. Any questions? Can I move to the next one? Do you want the board to stay still a bit? Okay, perfect. Right, so let's move to problem 3. Let's take a look at this other example. So we can apply a bit more what we've done so far during the presentation. So problem 3 says, using a cable with a tension of 850 newtons, a tow truck pulls a car 5 kilometers along a horizontal roadway. So question A is, how much work does the cable do on the car if it pulls horizontally? And then another part of the question is if it pulls at 35 degrees above the horizontal. And then in a same manner, question B is asking about the tow truck. So it says how much work does the cable do on the tow truck in both cases of part A. So question A is looking at the force that the cable is exerting on the car, and question B is looking at the force that the cable is exerting on the tow truck. So let's get into that. We have, let's just take note of the data here, the parameters of the problem. So saying that the displacement displacement is 5 kilometers and tension is 850 newtons. And we have, let's just have a nice diagram here. We can say this is our car. And let's say we have track here. Truck. And this thing is connected in some way with a rope, something. At first, we have that, and then on the other case, we have that with, let's call it theta equal 35 degrees. Right, so for case A, question A, we have theta equal 0, one case, and then we have theta equal 35. Right? Those are the two cases. And it's asking about the work that the force, of course we have a force here, right? The tension that the rope is exerting on the car. And we have, for that, we would have, for the first case, we don't have tension and displacement pointing to the same direction. And for the other one, we will have tension, tension and displacement with that angle there, which is theta. Right. So basically, we are changing the angle there, and of course, we would have a variation in the work that it's performed. And which one do you think will be greater? The one which is totally horizontal, or the one which has some angle there, in this case 35. So if you think about that, it will be easier to pull the car, right? If we have a horizontal line, right? Because then all of the tension that we are applying will be dedicated to pull that car, and we will perform we will maximize the work that we are performing there. Can you see that? Can you see that? Why is that? I mean, we will have basically the cosine will be modulating the actual the total work we're getting, right? And if we do the cosine of 0, then we will have a 1. right? And if we go sweeping angles from zero to, let's say, 90 or something, then we will go from a cosine of 1 to a cosine of 0. And the work will be greater if we are just pulling fully horizontally. I mean, it's in line with the intuition, right? It would be always better to fully pull from the car, not in an angle. So we translate that to math here, to calculations, then we'll have this, right? So we know that work is F D. Well, yeah, here I forgot to mention that here I use D for the displacement. Well, you can see that as FS, sorry. So that could be dependent on the mood of the of the person solving the problem or actually talking about it, but we know that it's the displacement, right? And that's equal to F D cosine of theta, right? So we can calculate that, and for theta equals 0, we have work equal 850 newtons time 5 × 10⁻³ meters cosine of 0, and that's given 4.25 10⁶ joules. And for theta equals 35, we have basically the same, 50 meters cosine of 35 equal, let me calculate that. Yeah, forgot minus. Yep. So 3.48 10⁶ joules. Right. So we've calculated the work performed by that, but those two by those in those two cases. So we have less work pumped into the system if we're pulling with some sort of angle, and the displacement is fully horizontal. I mean, the car won't lift, right? The car will go forward. Any questions about that? Any questions about the consideration of the angle, the directions? Okay, so let's look at question B. So question B is asking about the truck. So the force that the truck is being subjected is the tension, right? It's the same. It's the same magnitude, but it will be pointing to the other side of the movement. We'll be pointing left, right? Because we have the rope there, right, which is connected to the car. It's pulling the car. Perfect. The car is experiencing that tension pulling from it, and then the truck will experience some opposite direction force, which is pulling it back, right? So for the truck, then we would have, let's say, B here. For that, we would have in the case that theta, right? The first case, theta keeps being 0 if we're looking at the, our system of reference. But now the tension is pointing the other way. So if we, let's say we graph that, then we'll have the truck moving that direction, but the tension will be pointing this side, right? So we have D here and the tension pointing to the other side. So if we want to calculate the angle, then this thing would be 180, right? Because the truck is moving to the right. The truck is going forward, but the force is pulling back. So now you can see that we will have a big difference in there. Well, big difference. I mean, a sine is a big difference. And for the other case, if we had an angle of 35, then this thing will be pointing that way. Displacement will keep going forward, right? And then we can calculate that, right? And you can see that it's not 35, right? And then we can calculate that if we do the first one, we have the work here, which is 850. 5, 10 to the third meters, cosine of 180. And this is minus 425. 10 to the 6 joules. Right? And check, but I think it's, yeah, same. Okay, so here we would have work. I was just checking the actual numbers, so you don't get those wrong, but yeah, they're the same as what I wrote in the answers, so it should be fine. Of course, you can always check the numbers and tell me if you find that something is not, because this is calculator, and sometimes you can round differently, so we can have some discrepancies on the numbers. So 850, 5, 10 to the third meters, and cosine of what? So we have 180, and we have that. So the angle here is 35. We have 35 there, right? So we have that 215 here. And that's minus, let's do all of 50. Yeah, minus 3.48 10 to the 6 joules. Right, so we got two minus signs there. So this is 215. The whole thing from here till there. Okay. Any doubts about that? Any questions? Will a rope usually always provide equal tension to both sides? Good question, Nathan. Yes, in this case, it's not saying it here because we are assuming it, right? But when the rope has no, it's a non-stretchable rope, so it doesn't have any elastic properties, then we will assume that it will translate the tension equally, right? So if it's exerting tension at some object, then the other object will experience the opposite tension. And that it's always valid if the rope is not being extended, right? So if it doesn't have any elastic property, then you can assume that the tension will fully translate from one object to the other. Although it's useful to think that it's not exactly the same force, right? It's the action-reaction pair, right? That it's actually being exerted on the truck. So we have the pulling force that the rope is exerting on the car, then the car is pulling from the rope, then the rope is pulling from the truck, and the truck, of course, is pulling from the rope. So there are two pairs of action reactions going on there. But in terms of magnitude, yes, we can say that the tension will be the same in magnitude and be fully transferred to the object which is attached to. Yes. Okay, so here you can see that actually, it makes sense that the magnitude of the work, the scalar, right? It hasn't changed in terms of quantity. The thing is that in one case we are seeing that the car is getting energy, right? We're pumping energy into the car's system because it makes sense. We're pulling from it, we're making it move. And on the other case, we have that energy is being drawn from the system because we're taking into account the truck, and it makes sense too because the car is experiencing some kind of drag, right? So the signs of the work will be negative. And of course, same consideration as before. If we're pulling with a full horizontal direction, then we have a higher let's say a higher yield of our force in terms of work and energy. And if we have some kind of angle, then of course we will be performing less work because you can see that we have a component of the tension, right? So let's say we have this tension, this component here, right? Ty, which is not performing any kind of work, right? Same in the case of the car, right? We have tension Y there. So those components are wasted in terms of work. They're not performing any work because they're perpendicular to the motion. Okay, let me just get that framed there. Any questions about this problem? If not, I'll move back to the PowerPoint and we can take a look at kinetic energy and we'll be done for today. Okay, Perfect. Let me stop this. And share the PowerPoint. Right. All right, so we've talked about the object moving. And sorry, we talked about the object moving, and of course, this will create some kind of velocity, right? If we are moving that object in some way, and we have some force, net force acting in that same direction, then we will have acceleration, and then that means that we will change velocity in some fashion, some way, right? So let's take a look at this example. If we are pushing that object, let's say in here, pushing that object to the right, then we will be exerting a force, we will have a displacement. We can take a look at the normal and the weight, right? If we now drawing the free body diagram, and we know that those two forces are perpendicular to the displacement, so they're not performing any work, right? And the total work done on the block during that displacement will be positive. We are pushing it. We're creating a displacement, and we are accelerating that object, basically, right? So the block is speeding up because we have a net force pointing to the right. Okay, so let's take a look at the other example here. Let's say we have the block which is moving towards the right, and we are putting our finger there against the movement, so we are exerting a force pointing to the left, and now again, same thing, normal and weight, they're not performing any work there. And similar to what we've seen before, that net force will be responsible of decelerating the block. It will be responsible of depleting the velocity that the block is carrying, and then the block will slow down. And our work, as we've seen before, because we have a 180 degree in this case, for the angle, we will have a -1 in our calculation of the scalar product, and then the work will be negative, meaning that we are taking energy from the system. We're not pumping energy into the system. And it makes sense that the block will lose that velocity and it will stop. So you can see that there must be some kind of relationship between the quantities that we are defining now, which are work, energy, and the actual velocity of that block. And the last example here, just remember this is a frictionless surface, so there's no interaction. We're not considering any interaction between the plane, the floor, and the block. So if the object is moving in that way, to the right, and we apply a force which is pointing down, perpendicular to the displacement, then nothing would actually change, right? Because we don't have a friction force. So the fact that we are applying that force, that will make the normal bigger, right? To keep equilibrium, the y-axis won't change anything because we don't have friction, so we won't get a drag, a bigger drag pointing to the left, and then we won't have any net force on the x-axis, meaning that we don't have any acceleration, and of course we won't have a change in velocity in that sense, and then the block speed will stay the same. It's kind of crazy, but that's the case if we don't have any friction there. So you can see that if there's no work, see this work total is equal to 0 because there is no net force on the same axis as the displacement, then velocity will stay the same. So here we can see that there's kind of a relationship, right? Because we have work 0, velocity stays the same. Work negative, velocity is decreasing. Work positive, velocity is increasing, right? So if we want to formalize that, we can take a look at the equations of motion that we already seen that last week. Well, not that, the week before, actually. And if you recall this this expression here, which was relating the velocities with the displacement and the acceleration. So remember, this one came from combining the expression for the displacement and the expression for the velocity, and clearing the time and then replacing time in the expression for the position, then we can get to this expression here, and we can rewrite the acceleration as the difference between the squares of the velocities divided by 2 multiplied by the displacement. So just notice that this x2 minus x1 is nothing more than delta x, right? So that's the modulus of the displacement vector, right? So we have that block moving with speed v1, being displaced from x1 to x2. We have the vector, the displacement vector here. The block has a mass m, and then an x2 has speed equal to v2, right? And a net force acting in there. There should be some net force in order to the velocity to change and to create this acceleration. So we have this expression of the acceleration. Any questions about that? Can you guys remember that where's that coming from? It's coming from the straight line motion equations, actually. So if we now combine this result for the acceleration with the, what is this? This is the Newton's second law, right? So we have the net force here. So we have F equal to m mass multiplied by the acceleration, where that in the direction that net force is acting. So if we substitute the acceleration for this expression here, in terms of velocities and the displacement, we can write this. And if we rearrange that and we get S on the other side, so we multiply by S, we get F multiplied by S equals to 1/2. So that 1/2 is coming from this 2 down here. Mass V2 squared minus 1/2 mass V1 squared. And if you take a closer look to this, you can see that here we have the work, actually, because we're moving on a straight line. The net force is on the same direction as the displacement. Yeah, so we have cosine of 0 equal to 1. So F times S gives us the work that's being performed within that displacement. And so you can see from here that this looks like a variation expression of this quantity, right? Because you can see that, of course, 1/2 is constant, mass is constant in both terms, and we have the velocity, final velocity, initial velocity, right? Actually speed, because we're talking about the modulus. So final speed, initial speed. So we have a variation there between two time instants, right? And we can rewrite this as I said before, the total work equals to this two expression being subtracted. And from this, we can define what we call kinetic energy. And that kinetic energy will be defined as 1/2 multiplied by the mass of the particle multiplied by the speed of the particle elevated to the second power. So this is 1/2 mv squared. And let me continue here and take this expression, and if we replace this with K that we just defined, right, as the kinetic energy, then we would have kinetic energy at instant 2, at point 2, at the final instant of the movement, and then we will have of the motion, and then we will have kinetic energy, in terms of V1, that's K1, that's the initial kinetic energy. So we can say that the total work, it's basically the variation of the kinetic energy in our system. Okay, and that's a fundamental formulation in what it's the work and energy theory, and it's called the work energy theorem, right? It's a theorem. So work done by the net force on a particle equals the change in the particle's kinetic energy. Meaning that if we have work, then we will have a change in kinetic energy. And kinetic energy is related to motion. So there is some change in motion. Okay, so we are connecting the way a particle is being perturbed, and how the force that's perturbating that the way that particle is being perturbed by the force, and that's being reflected in a change of the motion in some matter, and we can quantify that with this that we have just defined, the kinetic energy. Okay, so we can see that if we have the total work positive, then the kinetic energy will increase because we have K2 minus K1. If this thing equals to something positive, then K2 should be bigger than K1, and that means that the kinetic energy increased. And that basically is telling us that we have something that changed, that had a positive change in the speed, right? Because we have bigger K2. If mass is the same, if of course this is a constant, then the only thing that can change is the speed. So if we have positive work, speed increases, kinetic energy increases. When we have negative total work, then the kinetic energy will decrease. This delta would be negative, meaning that K2 is smaller than K1, so the object is basically slowing down. And when this work is, the total work is 0, then there's no change in the kinetic energy. And for the work to be 0, then that means that the force is not acting in any components of the force, any projection of the force won't be acting in the direction of the movement. That doesn't mean that we don't have a force, right? It means that we don't have work performed from that force. So we won't have an acceleration in the component of the motion, of the direction of the motion is taking place, and it makes sense that the kinetic energy won't change because there's no change in velocity, right? And that would mean that we have constant velocity, and that constant velocity, of course, could be zero. Remember that. But that doesn't mean that the object is not moving. Okay, that's an important point there. So the fact that not having a change in kinetic energy doesn't mean that the object is still. It means that it has a constant speed. Okay, so I want to stop here for today. Tomorrow we will gonna get back to this topic and we're gonna look at some problems, and we'll keep defining some other relationships and between quantities and energies. But I just want you to take this idea today. So the work energy theorem, the total work performed by the net force equals to the change in kinetic energy. And that's something that will apply to all of our problems, right? So it's a really fundamental statement and pretty useful actually, because it will let us perform very simple calculations on complex problems where the equations of motion are complicated and are not necessary to apply if we want to calculate, let's say, the magnitude of the velocity, for example, and some other aspects of the movement. So working with energy is very nice in terms of simplicity and practicity for a lot of problems. Okay, let me stop sharing. Stop recording.